This conference will now be recorded.
Hello, everybody. Jordan Girth here from the National Weather Service Office of Observations. Hope everybody's doing well. We're here for Satellite Book Club, the seminar series. This is session number 46. So we're getting very close to 1 year of Satellite Book Club. And hope you'll join us for the 50th coming up in May. We got a great presentation today, an introduction to the VIIRS Snowmelt RGB. Dr. Curtis Seaman, who's a research scientist from CIRA, will be our presenter. Just a few reminders before we get started that the session is being recorded and there will be an opportunity for Q&A after the presentation. So please post your questions in the chat and we will field them in the order they were asked. We're always looking for future presenters, so if you have an application you'd like to share with your colleagues in the field, please get in touch with our TowerS team. And the training team can help create training materials that may be unavailable or you might be unaware of. And Brian Motta, the Office of the Chief Learning Officer, can provide you with information there. Just like to thank our TowerS team, particularly Kashad Bowman, who helps organize these, sends out all the mailers, does all the behind the scenes work, and Lee Byerly, as well as the Office of the Chief Learning Officer and the GOSAR and JPSS programs. Normally we would have a second person to do the moderating, but today that'll be me. And without further ado, I'd like to introduce Curtis, who received his bachelor's from the University of Michigan, followed by a master's and doctorate at Colorado State University, all in atmospheric science, and he's been working at CIRA since 2012. Most of his recent work is focused on multispectral satellite imagery products for hazard detection and the production of imagery products for CIRA's Slider website. He is a member of the JPSS and GOSAR imagery teams and lead of the MET-IMAGE imagery team, which are being reorganized under the umbrella of NESDIS STAR. Curtis, welcome to the Satellite Book Club.
All right, thank you for that. And before I get started, I would just like to acknowledge the contributions of Carl Dierking and Bill Line, who have provided some of the examples I will be showing today. And they were also instrumental in making these products available for AWIPS. So before I get started talking about the Snowmelt RGB, I'll just give a little brief introduction of VIIRS, because there are a few things that you can do with VIIRS that you cannot do with ABI, and the Snowmelt RGB is one of them. And so just a reminder here, these are the channels on VIIRS, that has higher spatial resolution than ABI. And we now have two VIIRS instruments in space, one on SUMI NPP that has been around since 2011, and the second instrument on NOAA 20. And these two satellites are flying in the same orbit. That is the 1330 local time orbit, so it comes across around 1:30 a.m. and p.m. every day. And since they're both in the same orbit, but separated by a half an orbit, you get two overpasses separated by roughly 50 minutes each afternoon, and again in the early morning hours. And so no matter where you are in the country, you're going to get at least two overpasses, and depending on where you are related to the satellite ground tracks, you may get three overpasses during a day. Now, if I ask people what is the number one thing you can do with VIIRS that you can't do with ABI, most people would probably highlight the day-night band, since there is no equivalent to the day-night band on any geostationary satellite. But there's another channel on VIIRS that is not available on any existing geostationary satellite, and that is the channel M8, which is at 1.24 microns. So it's in between the vegetation band, M7, and the 1.38 micron band, the CIRRUS band. And this channel is key to this Snowmelt RGB. And so, as I mentioned, this channel is not on any geostationary satellite, but it will be available on METIMAGE, which is the imager on the next generation European polar satellite program, which will be coming in a few years. And NOAA has plans to collect and distribute all of that data. So we're going to be focusing on one of the main applications of this 1.24 micron channel that is very sensitive to snow properties. And so what we have in this plot here is the reflectance spectra of snow as a function of wavelength and also snow grain size. Now we all know from experience that snow is very highly reflective in the visible portion of the spectrum. That's why snow appears white to our eyes. And as you get into the shortwave and midwave infrared, snow becomes very absorbing, and so it looks dark in the imagery. And this 1.24 micron channel is right in the middle of this transition zone from where snow is highly reflective to being highly absorbing. And you can see from this chart here that it's also highly sensitive to this snow grain size. As the snow particles get smaller and smaller, snow becomes more reflective at this wavelength. And conversely, larger particles are less reflective. And this is also true for wetness, that wet, heavy snow is less reflective than dry, powdery snow. And we are going to use this to our advantage with the Snowmelt RGB. So I'm going to just rehash everything I just said with a series of images, starting out with the red wavelength visible channel that everyone should be familiar with. You can see this scene covering most of CONUS with lots of snow over the northern plains and Midwest, which is uniformly bright because it's very reflective. As we move up in wavelength to 0.86 microns, the quote unquote veggie band, you can see that snow is still very reflective. Then we get to 1.24 microns, and now you can see that the snow is starting to become less reflective. And there's also quite a bit of variation in the reflectance of the snow across this whole scene. And you can also start to see this cloud here over South Dakota that you couldn't pick out in the shorter wavelengths. And as we keep going up to 1.6 microns, the snow and ice band, you can see now snow is very uniformly dark because it's highly absorbing, and the same holds true for the 2.25 micron channel. From an RGB perspective, here's what the true color RGB looks like for this scene. And again, snow is very uniformly white along with the clouds. And we can use an RGB like the Dayland Cloud RGB to discriminate snow from clouds. This takes advantage of that red wavelength visible band, the veggie band, and the 1.6 micron snow and ice band. So now we can discriminate the snow from the liquid clouds. Although ice clouds still appear in this same cyan coloration that the snow does. Now, if we replace the veggie band with this 1.24 micron channel, then you get what I am calling the Snowmelt RGB. And now you can see that snow is even easier to distinguish from the liquid cloud here over South Dakota, but it's also more blue in color than the ice clouds that you can see over eastern Colorado or even down along the Kentucky-Tennessee border. And you can see there's quite a bit of variation in the blue coloration that is related to snow age and snow melt. I also want to point out that a group at Meteo France has developed their own version that they just simply call the Snow RGB. that also uses this 1.24 micron channel, and they end up reversing everything to make the 2.25 be the blue component and the veggie band as the red component. And now you can see that snow varies in color from orange to dark red. It provides similar information, but just a different coloration of the snow. And just from the people I've talked to around here, at least at CIRA, seem to prefer the blue coloration to the Snowmelt RGB. But if you like viewing snow in orange and red, then you're certainly welcome to use this Meteor France Snow RGB as well. And we're going to zoom in here over this region of southern South Dakota. You can see this bright orange feature showing up, which is also a light blue feature in the Snowmelt RGB. And this feature is very difficult to detect in the true color or the dayland cloud RGBs. And what you're seeing here is a swath of fresh snow that's visible on top of old snow. You know, as you think about it, you know, when you have small snow particles, or you know, a mix of snow sizes, the smallest particles are going to be the first particles to either melt or sublimate, and that snow grain size is gradually going to get larger with time as a result of that. And that is what allows you to see fresh snow on top of old snow. But generally speaking, the Snowmelt RGB is very similar in appearance to the dayland cloud RGB, except when it comes to the properties of snow. So we have very whitish, low-level liquid clouds. We have the same cyan coloration to thick ice clouds. But now you can see that the snow varies in color from a light blue over the Dakotas and western Nebraska to a very dark blue here along the Iowa-Missouri border. And this is from a case back in December 2020. And this dark blue region is actually a region that saw quite a bit of mixed precipitation out of this storm system off the eastern side of the image. And so these areas saw a lot of freezing rain and sleet, and as you can imagine, wet snow with temperatures near freezing. And you can detect that as being distinctly different from the lighter, fluffier snow off to the north. And so we're finding that this is another application of the Snowmelt RGB. Here is a case from January of 2019 where a high impact nor'easter went through New England, depositing a lot of snow in northern New England, which maybe is a little bit more difficult to tell because forested areas can obscure the signal of snow on the surface. But this storm also provided rain along the coast and a significant freezing rain event in between. And you can actually see that as this dark blue line that stretches from northern Rhode Island into northern New Jersey. And so this was a very significant ice event. And if you zoom in just over Connecticut, you can see that S-shaped curve in that region of ice matches up very well with a map of power outages that came as a result of this event. Here is an example from back in January of this year, just looking specifically at snowmelt. And so I'll focus your attention first over Nebraska and Kansas. And we're going to look at two images here. The first is the NOAA 20 overpass from 1910 UTC. And the second image is roughly 50 minutes later from Sumi NPP. And as I toggle back and forth, you can see that not only does that snow over the Great Plains get darker with time, but you can see the edges of the snow field are receding as the snow is melting down there. and temperatures on this day were in the upper 30s to low 40s over that region. So you had a significant amount of snow melt, to go along with that sunshine. If you look farther north, though, up along the Canadian border, as I toggle back and forth, you'll see that snow does not really change in appearance between the two images. And that's because it was much colder up there. Temperatures were in the single digits and teens, so there wasn't any snow melt going on. And so the snow maintained its light blue appearance. Here's another image from earlier this year. This is the middle of February, and we should all remember that high impact Arctic blast that impacted Texas in the middle of February. And so this is an image from that case. But we're going to zoom in on 3 different regions from this one VIIRS overpass. Starting off down in Texas, you can see that there are some regions of darker blue coloration in here. And these actually line up very well with where there were surface reports of freezing rain and sleet during this storm system. If we look now over northeast Colorado, where I live, you can see that the snow is very uniformly light blue in color. That's because this storm was very cold. Temperatures were in the single digits above and below 0. And so we had, very, very fine grained snow up here. And as an interesting side note, you can actually outline the urban area of the greater Denver metro area here sticking out above the snow. And also the line of cities from Boulder to Longmont and Greeley up here. Fort Collins, where I live, appears to be under this cloud, and so it doesn't show up quite as well. And the third region from this same overpass we're going to look at is up over Oregon. You can see that the snow is much darker blue here in central and eastern Oregon. And that's because they missed out on that Arctic blast of air, and they had temperatures in the mid to upper 40s on this particular afternoon, which caused quite a bit of snow melt. As I mentioned, Carl Dierking was primarily responsible for getting this product into AWIPS up in Alaska. And so he provided me several examples up there. And so this is a case from March of last year. And you can see, again, everything that I have been highlighting. These valley areas that have warmed up above freezing during the afternoons have much darker blue snow. But the higher peaks, particularly in the Alaska range here, have very light blue snow, where it's a lot colder and you don't have any snow melt going on. Here's an example that Carl Dierking provided me from just a few weeks ago. So this is the first week of April. And in the upper left, you see the VIIRS snowfall rate mosaic, indicating that on April 3rd, the western and central portions of Alaska got some snow. And if you look at the Snowmelt RGB the following day, after the clouds cleared out, you can see these bright streaks across the snow that show up even better when I zoom in here. And so these are areas, again, of fresh snow falling on top of old snow. Here's an example looking at southeast Alaska and Yukon Territory here with the glaciers of Wrangell St. Elias National Park. And this is at the end of July in 2019, shortly after Carl Dierking got this product up and running in AWIPS. And you can see that these glaciers are very dark blue since it's the middle of summer and there's a lot of melting going on those glaciers. Then, at the end of February, beginning of March, we were able to produce tiles for the VIIRS Snowmelt RGB on our LDM server for CONUS use in AWEBs. And this is an example that Bill Line put together looking at the upper Midwest. So this animation starts out on February 28th and runs into March 2nd. And you can see that at the end of February, this storm system deposited a broad swath of new snow from South Dakota up into northern Wisconsin. And over the subsequent days, this snow started to melt and became darker blue in color, matching the older snow down in Iowa and southern Wisconsin. And Bill Line also put a blog post out on this case if you want to read about it later. I also want to mention that we do have the Snowmelt RGB on our slider website. So you can see the URL down here if you're interested in looking at global VIIRS imagery. And this is a case just from last week, looking over Hudson Bay. And this image here has the appearance of rain falling on top of the ice sheet as you get these streaks of dark in what was formerly very uniformly light blue colored ice sheet. Of course, we don't have any surface observations over Hudson Bay to validate that, but that's my best guess as to what happened here. And you can compare that with the day snow fog RGB. I know this is another popular RGB with places that get snow. And I just want to highlight that, yes, you can see a little bit of darkening here in this swath with the day snow fog RGB, but it does seem, the signal seems to stand out a lot more in the Snowmelt RGB. And so now I will wrap it up here with our look at snowmelt from satellites. I do just want to highlight that we have a quick guide out, thanks to help from Jarrell Torres for putting this together. And I mentioned the link to Slider. And if you're interested in receiving the Snowmelt RGB through our LDM server, you can contact me or Bill Line or Jarrell Torres. We all possess the AWEBs configuration information that you need. And if you have any questions or concerns about the Snowmelt RGB up in Alaska, you can contact Carl Dierking, who is responsible for that product. And with that, I would be happy to take any questions.
All right, thank you, Curtis. Great presentation. Appreciate that introduction. We'll go into questions here in just a moment. Please feel free to submit your questions in the chat, or if you want to ask it verbally, we can also arrange that. Just indicate so in the chat. Before we go to the questions, I'll just do a reminder for next week, Thursday, April 29th, again at 12 noon Eastern time. Sharon Sullivan, meteorologist from the Albuquerque, New Mexico Weather Forecast Office, is going to discuss the use of satellite imagery to capture dust plumes. So look for an email regarding that. Feel free also to contact the Tower S team, Lee Byerly or Kashad Bowman, for questions about the Satellite Book Club or any configuration of satellite products at your office. So with that, we'll go to the questions now. We've got a few coming in, and you'll also see the survey there from Lee about the Satellite Book Club. Everybody's asking for your opinion these days. We're no exception to that. First question from Bill Schoberg. He says, it appears that you can see river valleys as dark areas. After a snowstorm in areas where rivers are not frozen, will the dark blue show up immediately?
So the dark, I mean, water appears very dark in this RGB. And so yeah, I mean, water areas do show up dark, and lower elevations, may end up experiencing melting first. And so, yeah, I would expect that areas in and around rivers, you know, they may get the melt sooner.
Okay, thank you. And Bill also recommends that a couple of forecast offices could help validate this RGB over the next winter. And I think some already might be up in Alaska. But I have a few questions for you, Curtis, as we wait for others to potentially come in. You know, one of the things, anytime we use the near infrared, subject to solar illumination. So I'm wondering, particularly in the winter seasons, if illumination angle does affect the use of this product and the ability to distinguish the different snow types.
So certainly this product only works during the daytime. And so, you know, up in Alaska where it's nighttime for most of the winter, this maybe is less useful up there. But as far as viewing angle dependence, it seems like the background vegetation, one of the things that I've noticed is that as you get later in the afternoon, the background vegetation seems to brighten up over the course of the day. And so that may have some impact on the coloration of the snow. But I think that that the general trend from light blue to dark blue still holds up no matter what time of day you're looking at it, as long as the sun is out.
And following up on that, you know, at GOES-R, we have the 1.61, 2.25. I think you talked about that and even compared it. With GOES-R, I think having access to those those channels can be helpful. For example, some of the cases you showed about freezing rain. You know, we've seen cases where freezing rain on top of snow is identifiable in the 1.61 micron, for example. I'm just wondering, noting that the 2.25 is related, the reflectance is related to cloud particle size, if you've tried to derive or simulate a 1.24 using 1.61, 2.25 bands that all our meteorologists would have access to from GOES-R.
That's an interesting idea. I have not done anything like that. But just to reiterate from this plot, you can see that at 1.6 and 2.25, you do have sensitivity to snow grain size. So it is possible that you could use one or both of these channels in place of the 1.24, you know, when you don't have it. And I think Bill Line may have actually come up with an example where he used the 2.25 in place of the 1.24 in the Snowmelt RGB, and you could still detect things like freezing rain and snowmelt, but 1.24 is definitely the most sensitive channel.
Right. I mean, you certainly have a larger contrast there, but that'd be good to look into, because I think as we move into GeoXO, we make those band decisions. If the 1.24 is one that we need to have, or if it's one where we can get the information from bands we already have, you know, we can't necessarily have an infinite number of spectral bands. A few questions have come in here, and good ones. George Perry asked, would trees in mountains impact the ability to monitor snowpack conditions there?
I think any time that you would have something that casts shadows on top of the snow, it is going to affect the appearance of the snow. And so if you have mountainous areas, maybe we can see that in this image here. So if you look at the mountains in western Montana here, I mean, these are all covered in forests, and that's primarily what the satellite is seeing. It's seeing the trees and not the snow underneath it. So that is definitely something to keep in mind.
I think Scott Carroll had a very similar question about variability in terrain and mountain size and whether that affects the usability in mountainous areas.
Yeah, But one of the things that we're hoping to find, I mean, we haven't had the ability to really look at this closely, but it is possible that maybe, you know, in areas where you can see fresh snow on top of old snow, that may give you some signal for avalanche danger. And we'd be very interested to validate this product with respect to that capability.
Yeah, that's interesting. Thanks for bringing that up. And it just looks like a comment from, I believe that's Scott Lindstrom. You don't need mountains to have trees. Look at northern Wisconsin on March 11th of 2019.
Yeah. So you can see that in this image that as it gets more forested, you know, the signal of the trees dominates over the signal from the snow.
Yeah. Okay, we'll leave it open for questions. I just have one final question here. Maybe you could tell us a little bit more about Met Image, since that's not something our field offices aren't necessarily aware of.
Yeah, so Met Image is going to be a very VIIRS-like, or maybe even more MODIS-like imager that will be launched, I think, in 2023 or 2024 by the Europeans. And so that's going to be a polar orbiting satellite in the mid-morning orbit. So it'll have about a 10:30 local time overpass. And it has a lot of similarities to a VIIRS, but it will also have the water vapor channels on it, and it will also have this 1.24 micron channel. The main other difference with VIIRS is that it will not have a day-night band. But NOAA is planning to collect all of that data and distribute it out to the Weather Service.
Okay, well, yeah, I don't know the plans for Met Image are finalized yet as far as what bands forecast offices might receive from Met Image, just as forecast offices have limited access to VIIRS currently. But that's something we'll certainly be thinking about as we go through the Met Image program evolution. All right, well, seeing no other questions, I will thank you again, Curtis, for your presentation today. Hopefully everybody found it useful, and hope the snowmelt season goes well and we have a nice transition into spring here. Thanks for our audience for being with us today as well. Again, I'll just reminder, next Thursday, April 29th at 12 noon Eastern time, we're going to be talking about dust plumes with Sharon Sullivan from the Albuquerque Forecast Office. As always, please feel free to get in touch with our TowerS team if you have questions about the Satellite Book Club, or you're just not finding the satellite products that you think you should be seeing in your AWIPS. We're very happy to help you. We are standing by for that. So until next week, stay well, everybody. Thanks for being with us, and hope you'll catch us next week. Bye now.